Chapter 1, going one off. We're CSC 102. This is Computer and Information Technology. And you guys can't see. There we go. All right. So, Chapter 1. What we're going to be talking about, go back to our slide, is computers and information processing. All right. So that's going to be kind of the overall theme. So, the first thing is recognizing a computer. So, wonderful game here is what is a computer? Most things that we are interacting with that are electronic today are computers at this point, right? It's like your cell phone, your digital camera, if you have something, your laptop, your car. If you have an infotainment system in your car or a touchscreen in your car, that is a computer of some sort. Even just your standard radio in your car, you could argue, depending on how they're made, is a computer. So what is a computer? A computer is a programmable machine that converts raw data into data can be words, pictures, or sounds that represents facts about anything. So unprocessed or raw form. Data is going to be unprocessed. It's information coming in. Or not information, data coming in. Now, information, on the other hand, is data that's been processed. So it's now in a useful form. So again, that could be, all the colors of the rainbow. So whatever the case is, whatever you're looking at, that is, the data, and then the computer's processing all this information that's coming to it from over the internet to show you the slide video stream. That is the information that it is actually processing. There's a lot that goes on with a computer actually. Now we have ambiguous computing. ICUMP. All right. This is also known as invisible. So this is technology that receives into the background. It would be like the radio in your car. That would be ambiguous computing. It's something that is a computer, but you don't even realize it's a computer that you're interacting with. I'm just interacting with the radio, but again, there's lots of processing that's happening in the background that you don't really even know with. And so this is because technology is so prevalent that it may not be identified as a computer. Not something we think about. When someone says you have a computer, that you normally think laptop or a desktop. You're not thinking, oh, it's my cell phone in my hand. Yeah, it is. It is doing all sorts of processing. Right. Some other computers that you might not think about, digital signage. If any of you guys drive down 40, there's that giant digital billboard. Well, that's ambiguous computing. There's a computer that's doing that, picking which thing to put up, how long to put it, all those little things. If you pay with the tap of your credit card, that's another one. Smart devices, remotely turn outlets or lights on in your house, change the temperature of your thermostat, or whatever the case is. Those are all computing. We also have IoT, or the Internet of Things. It's still a pretty big buzzword, I'm going to say today, but it's not as big as it used to be. This is when we connect physical things to the internet. This goes back to like being able to turn your lights on your house on or off remotely. Some people say that is an absolute joke. There's no need to be able to do that. And I can't really argue that statement with. There's really probably not really a great need to be able to do that for most people. For some people, like large businesses and things, where the whole building is networked together, they can save themselves probably thousands of dollars a year by knowing, oh, there's somebody in this room, so we need to turn the HVAC on or off. Or the lights are on. Why is the lights? The one's in there. Okay, turn those off. So by connecting these things to the internet, or to at least servers locally, they're able to save money. And the same thing technically could be done for your house if you set things up correct. Now there is a lot of setup involved. It's not as simple as, look, let me just buy a few devices, plug them in, boom, we're good to go. No, it's like, okay, we need to have these devices, might need to have presence detection in each room, so that way you know, okay, there's someone actually in there, the lights on, or okay, we know we can turn those off. Same thing for the HVAC controls, maybe you do it by floor instead of by room, but still have those controls. So by connecting all these things to the internet is actually it can be very useful. And I will say that my parents and I both have our thermostats on the internet. I can turn the heat on my house on or off, and it's absolutely wonderful for when you go on vacation. You leave for vacation for a week. You don't want to have your air conditioning running the entire time that you're gone. That's just a waste of money. So you turn that temperature from instead of having it set at 75, we'll set it to 85. So keep the house reasonably cool, but not as cool. So you're going to save all that money, but it's not much worse than getting home from a long trip to a house that is super cold or super hot. It's just not very enjoyable. So being able to then say, okay, we're 2 hours from home, turn the air conditioning back on, you're then able to do that and say, okay, now nice and comfortable when I get back home. It's definitely convenient to have that. It's not nowhere near a necessity. Some other Internet of Things that we might have is locating devices. All right, so we are kind of talking about monitoring, controlling things. Locating devices is also. We also have embedded computers, all right, which I would say is that green board on the bottom right corner, or that bottom picture that you guys are seeing. I would say that is probably an embedded computer or something. And embedded computers are just specialized computers. They are traditionally part of another device, such as a car, gas pump, home appliance. Right? So they are just built into these things. So yes, your car most likely has a computer running it. I don't remember at what point that the government said that all newer cars have OBD2 abilities for reading and writing and diagnosing and things like that. But it is something that they definitely said this has to happen now. So there is some sort of computer in your car. You can check your transmission temperature, your oil temperature, your fuel, your miles per gallon, if there have been any misfires on cylinders, if there's oxygen consumption that's reading something. So there is an embedded computer in there that's taking all that data processing, or all that information processing. That way we can actually do something with it and understand. So, but yeah, anyway, most things are going to have some sort of embedded computer anymore. And these embedded computers are getting rather complex in the long run. 2 years ago, we had a Chevy Equinox, and every month I would get an email letting me know the health of my oil level. You've got 20% oil life left, and oh, your gas is this, and your tire levels are that. It would just tell me all these things. There's a recall on it. It would let me know. Like that's starting. It's going to be kind of creepy that it's emailing me all this. Now, what all is it actually telling Chevy? Much more does Chevy know about my car than I actually my garage, but this is how the world is working. So we are embedding things, and it's just, to some extent, it's really convenient to have all that information being processed in here and just emailed to you. If you're not a car person and you don't pay attention to your car, having an email saying, hey, it's time to change your oil is very convenient because you don't have to think about looking in your car or whatever the case is. And at the same point, it's, for some people, creepy. So definitely a little bit of a give and take going on with our embedded computer. Then we have convergence, which is the integration of technology on a multifunction device. So it's what all can you do on your cell phone? Right? Think about that. Your cell phone, it used to be you made phone calls on it. You could send text. It wasn't very nice, right? You had to do T9 texting, and some of you may or may not ever had to deal with that. You had to like hit. You wanted B, so they did the 2 button twice. Pressed it once, it was A. Pressed it again, it was B. You could type something else. You could type out that way. And some people were extremely good at this. Like they could send text messages without looking at their phones. And I know people that would like do that. Yeah, I can do that. They would just put their phone like behind their back. They could send out a perfectly legible text message because they did it. But nowadays, you get your email, and it's not just your email; it's your work email, your personal email, maybe your other personal email, whatever the case. You can browse the web. You can edit documents. You can listen to music, pictures. You can have that direct to where you're going. And you can even, if your phone supports it, pay using your credit card. So there is just a boatload of things that we can now do with our phone. So it's now a multifunction device. Right? It used to be like you forgot your phone at home. You're like, okay, whatever. Can't make your phone calls. People won't know where I am. I can't talk to them. And man, let me tell you, that used to be so. Nowadays, you leave your phone at home, and you're like, oh man, I can't pay for my food because my credit card's on there. Credit card, my wallet today. Whatever the case is. And I have done that. I'm like, I forgot my wallet, but my phone's on my credit card's on my phone, so I'm still able to pay for whatever it was that was there as long as it's not also store support pay with the and the last song for recognizing computers is what is green. This is the efficient and eco-friendly use of computers and other electronics. Using computers to be more efficient, basically. And home automation is a great example. If you don't do it correctly, it's a great example. So it really just kind of comes down to also smart appliances that monitor signals smart grid, mainly such as power conservation movements. And they've been doing that for a while, actually. There are, in some locations, not all, some power companies will give you a rate cost of electricity, heating or cooling time. So basically, they're like, okay, if you allow us to remotely disable your HVAC units, air conditioning all 24/7, we'll let you only charge you 10 cents per kilowatt hour instead of 13. So it's going to be a big cost savings to yourself. And what they're doing is they're saying, we are approaching maximum capacity of the grid here. We need to turn air conditioners off. What they do is they turn half them off, an hour, and they turn those on, and they turn the other half off. They just alternate back. Now, yes, your house may get a little bit warmer than you might desire, but it's still it's saving electrical grid for possibly going. So, very powerful thing for them to be able to do, and as long as we're able to take this in quality way, not just dumping it. But, yeah, okay, we can do this, and now taking. Now, how do the computers process it? So the first step is raw data enters the system. So what type of raw data might that be? That could be text that you're typing as a computer. It could be numbers on your spreadsheet for budget. It could be the data from individual pixels. Whatever information is coming through, the microphone on this computer that you guys are hearing me talk through, that is raw data that is coming into the computer. Okay, I know this is supposed to be audio data and it's processing. And it's amping it up, it's lowering it down, it's doing whatever it is that I think it can do. So very, very powerful data that's being processed right now. Okay? So we take that data, now we process it. Right? Now we're into the processing stage. Computer programming changes the data in the stage and gets it ready for the. So we take the raw data, process it into. Now from there we have two different options where we can store it. If we're storing it, that just enables you to save information in a digital format and retrieve it later. And the key word there is digital format. Most computers, not quite all, but most computers are saving everything. They are processing things, which is both wonderful and horrifying. If you have this beautiful sine wave audio, the computer is actually saving the steps. So it's not this beautiful, great thing. It's a whole bunch of like little itty bitty steps. If I were to make that bigger, now we do that faster and faster and faster. Now do that so that way it is cleaner and smoother and it looks better. So that's why we are processing. So it's definitely a bit of a give and take going on. Even if we're just outputting the data, it's output the data for you right now. It's transfer the internet over your speaker. And it's digital data that we've little steps that we are processing so quick that it seems like it's a beautiful curve and it sounds perfect fine to you. So we have a storage option, and if we're not storing it, if we're not, we're also outputting it. That's when the process data is returned. Right, so we already talked about the audio that you see. On the spreadsheet, it could be subtotals or totals of the budget. It could be your document finding words. It could be the screen that you're looking at. That is, every pixel of that is data that your computer has processed and given to something so that way you can have a picture with just text on it. So there is a lot that happens in our processing. All right. Now, I just briefly talked about bits. A bit. So computers use the binary system. This is a base 2 system. You can think of this as digital switches. So every bit has two possibilities. So possibilities are a 0 or a 1. Those are our two possibilities. Every bit. And that's it. So for our traditional math system, we use base 10, 0 through 9. There's possibilities for each spot. But for computers, there's only one. It's either on or it's off. True or it's false. Those are the only options. Now, if we have 2 bits of information, we now have 4 possibilities because the first spot can hold a 0 or a 1, and the second spot can hold a 1. If I break that all out, you would have 0, we have 0, 1, 0, and we have 1, 1. All right. So there's 4 different possibilities. That'd be power of 2. So you take the number to determine how many possible combinations are. This first spot is how many different possible combinations there are for each spot. Second number, the exponent, is divided into 2 possible combinations per spot. And there's 2 spots. Squared, that's 4. 2 times 2 is 4. 4 times 2 is 8. That would be 5. Here. Now, as we continue up, they've defined that 8 bits is 1 byte. And there are 256 different after that. But we do have that. Now, one interesting thing here is, yes, there's 256 combinations, but the possible numbers are 0, 55. So since 0 is the first one, that would be our first combination. 256 different. And over here on the left-hand side of the screen, I have your prefixes. You've probably heard of kilo, mega, giga, and tera. Files 3 megabytes, whatever the case is. We are to the point, and especially with spinning hard drives, that terabytes are kind of standard. I know at home that I have a terabyte hard drive in my location for all of my data. Can you go bigger? Oh yeah, you can go up to petabytes. So we can kind of just keep going and going and going and going. But for the most part, kilo, mega, giga, and tera, you should know. It's 3, 6, 9, and 12. Each time we go up by 3. The initial, without a prefix, that would be 10 to the 0. Then we go up to 3, so plus 3, then plus 6, and plus 9, and plus 12. So as long as you can remember kilo, mega, giga, tera, and you increment by 3, you're pretty good here. Yeah, so they just keep going. All right, now, most people, average people, have no need for a petabyte. We don't probably never get there. Every single document, every single file, maybe you'll need a petabyte. And I should say, though, that's current. Even if you have boatloads of music, TV shows, movies downloaded on your computer, they're probably not. Terabyte? Yeah, oh yeah. Definitely get to terabytes. Terabytes. Biggest. That's not surprising. But petabytes, probably not. Now, the one caveat to that is if you decide that you're going to become a YouTuber, then you might need more than a petabyte. If you are constantly recording videos and then yeah, you might get a petabyte. But most average people, they have no need. Now, someone did ask, so who uses more than a petabyte? This would be large companies that are storing massive amounts of data, like Google. I'd be very intrigued with storage Google actually have. How much storage? Google, no, that's not. So Google holds somewhere around 10 to 16 exabytes of data. They are very into this category, right? So, you know, my random web search set, right? So that is a lot of data. They probably, even though they have 10 to whatever 15 exabytes of data stored, that could be that, you know, that's one copy of it. Multiple copies of those run around the United States of the world. So that way you're not, when you're like, hey, I need access to my data, and I'm in California, they've got a copy there. And then, if something does, like, server facility for them does burn down, they've got a copy here and a copy there. And, you know, they might even have way more storage than we get. So that's your prefixes. Now, to kind of go along with going back to the whole wonderful world of bytes, right? To help computers work well, they have come up with a system that is called ASCII, ASCII, or American Standard Code for Information Interchange. And what this is it is a way to convert letters to numbers. So that way we can convert this. So this is a very standard system. It used to be, when I first developed it, it was a 7-bit system. So they had 128 different characters that they converted back. At this point, we've expanded that to 256. We're using 7-bits. One of those things. I should have my slide. I don't. There we have the ASCII. So if you wanted to send a letter in, that would be the equivalent of 77. If we converted 77 from decimal, I'm running the Windows calculator, 77 in, you can see in binary that's 010011. So that would be the conversion. So that is how computers, every time you type out the letter N, the M, capital N, your computer actually says that's 77, that is 010001. So that's how ASCII. Right, and this is the 128-bit one. But they're all standard. Very convenient. Yep. And then we also have Unicode, which extends the ASCII set. It's codes for over 100,000 characters. Now, this is important because when your computer is trying to decode a file, it needs to know, is that file in ASCII or is that Unicode? That way it can decode things correctly. Kind of like if you ever try to open things in a text editor. These files open in a text editor. But a lot of times you will see absolute gibberish going on there because the computer doesn't know how to decode it. But you can open a lot of things in a text editor and look at them and edit them and things like that. So it is a very important thing. The Unicode system is used for languages like mechanical systems, characters. And there are some languages that have more than 256 symbols, so they have to use. It's a little bit of a given. So the evolution of the computer back in the 19th century had the analytical engine. It was a mechanical computer design that relied on punch cards. If you've ever seen a punch card, this is a punch card, that top right picture. And each one of these different rows, they punch this in. This could be the design of a well, okay, now it's red, now it's blue, now it's green, so that's how this punch card could work. Way back in the day, my parents wrote computer programs on punch cards. That doesn't. So kind of crazy. So Ada Lovelace, she was the first computer programmer to write a program for this computer. Unfortunately, the technology to build this computer was not available in this era. The computer program could not be tested. So he came up with this idea and said, this is how it's going to work, but they couldn't actually. Then in 1936, we got a Turing machine. Turing. He developed the concept of machines called Turing machines. We also have the Turing test, 50, and this determines the machine's ability to display intelligent behavior. This led to the concept of artificial branch of science where computers display human. So the Turing test is we've overall moved away from it because AI is good at that. But that was the first type of test that was like, okay, how intelligent is it? The other thing with AI is not perfect. I've heard this about many times in classes, but It is far, far, far from perfect. You might find an AI that is really good at one thing, but it's really bad at everything. Good at everything. That one thing it might be good at. I've tried using AI for things, programs with it. Like, here's what I want it to do, and it spits out information, and I try to run the code, and it's like, nope, we can't run that. I have to go figure out why you can't. So, and then I've been able to tell the AI to always include some statement because that statement is running. You should have known this about programming one. It's kind of interesting. But anyway, after that, we have the first generation of NAC, which is the electronic numerical integer and computer. And they used vacuum tubes and manual switches to process data. The first computers were the size of a room, right? So you physically walked inside of the and the first generation computer weighed almost 30 tons, right? Those who don't know, a ton is 2,000 pounds. That would be 60,000 pounds. Now, in the 1947, 1950s, thereabouts, transistors led to the second generation. And this is developed. This enabled the development of smaller computers. So that is how we went from the group size of all these giant transistors to itty bitty little computers that were not quite there in second. But still, second generation transistors. Next, we had the third generation with integrated circuits, often called IC. Again, for those who don't know what I'm talking about, on this bottom picture, there's this little black box right there. That is an integrated circuit. It's, if you look really closely at it, coming off that chip. All that data signals or power signals or whatever the case is. Sometimes you'll see an integrated circuit. All you see is a black chip. You don't see those lines. Yeah, VGA, which is a ball grid array. So on the bottom, a whole bunch of little copper pads. There we go. Of little copper pads at the bottom that have little balls of solder on them. When they put them on the chip and they heat it back up, the chip melts. That solder melts, the chip kind of sinks down into place. Yeah. So this led to third generation, where I said that 1960s, and the computers are smaller, faster, and more reliable. Now we're to the microprocessor era, which is the 70s, where the microprocessor contained all the processing circuitry that it could be needed, also called the central processing unit. So it controls all the functions, processes all the commands. That's still the generation we're using them, but we're so there's also something that's called Moore's Law. Yeah. Moore's Law. Right. Moore's Law says that it's an observation, actually a law, that the number of transistors that can be put onto any integrated circuit would double roughly. Every transistor doubling the number every year. To integrated circuits that have processes better processes. So if you have a chip that's 1 square inch, so 1 inch by 1 inch by quarter, whatever the magic thickness is. Basically, 2 years later, that one chip will be twice as fast, twice as powerful. And we are seeing that with computers today. If you look at, remember that the first laptop I bought, 0.4 gigahertz processor. 4 years later, I had a quad-core 6 gigs of RAM. So I quadrupled my processing speed 6 times. It's kind of interesting, like 4 years. Huge. So just kind of something to think about. Now, some people do say that we are hitting the limit now with Moore's Law. Part of that limit is thermal. Technically, yes, we can shove more and more chips, little transistors into these chips so we can faster. The problem is that transistors don't create a lot of heat, but when you are shoving thousands or millions of transistors into these little packages, there is a lot of heat there. And how do we get that out? And that's where a computer gets in. But if you only have this little 1 inch by 1 inch square, only have that big of a square, my heatsink only can be so big, and the efficiency of taking heat off of that is only so efficient. Like we're hitting limits there. So it's like, yes, we can make these things smaller, but technically we need to make them bigger so we can get heat off of them better. So cooler so they run better. Viable. So just kind of an interesting thing that works. Now we do have personal computers, right? And they are designed to be used by one person at a time. So if you look at your laptops, your desktops, your computers you're sitting at right now, those are all personal. Personal computer is designed to be operated by a single person at a time. Now, of those, I would argue desktops are my. They offer speed, power, and upgradability for the lowest cost, and I am nothing but cheap. Possible. So I like desktops because of cheap they are for what you get. I also like take my video card out, put new one in after. Doesn't happen. 6 years and I'm still rocking that video card. I'm rocking it for everything. Right. But anyway, I like to be able to upgrade things, add new hard drives, add new video cards, or capture cards, or whatever cards it is that I need at that specific point. Now, under the desktop computer section, there are kind of two different subsections. We have workstations, which are often found in businesses. These are traditionally higher-end computers. They can be costing multiple thousands of dollars. They might be attached to a network. At this point, everything's attached to it. Just about everything. Not guaranteed, but you're all like having the network, like having internet, like to print things and having a printer attached to our computer. We like to apply files. So probably on some sort of network, some sort. All right. So and you know, computers they're getting pricey. All right. For a like pretty darn good gaming computer nowadays, you're probably looking at $1,000 to $2,000. Sorry. Can you get it for cheaper? Yes. And can you get them like an older generation and still be just as good as a new generation? No, it will be just as good, but it'll probably handle good for now. Definitely worth looking into retired workstation computers. Because they top of the line when they buy them, and then they get rid of them 4 years later. So you're like, okay, that's only a 4-year-old computer. It was top of the line when I bought it, so it's now a mid-range. Definitely worth looking into. And to go along with that, you have your all-in-ones. So all-in-one computers integrate the system unit with the monitor, and it's often there to save space. This also does save some cost, but I really there's two main reasons. One, it limits upgradability. Okay, might be able to change your RAM, maybe not. You definitely can't change. Probably doesn't have a dedicated graphics card. It's probably using most likely can change the hard drive out. But it's like this is what you get. Another thing I don't like about all of them, they encourage waste because like okay, I bought this computer, I've used it for 10 years or 8 years or whatever. Oh, time to get a new one, and your monitor also has to go out the door. Not like, well, I can still use the monitor for something. I use it. But I have some very old computer monitors, and they still work perfectly fine. Are they 4K? Oh, I don't need 4K. It might be 1080p or something like that. It might be 7. Guessing at 1080p. But I don't need it. It's just a little side monitor for me that I have a Word document or whatever on. It doesn't need to be a 4K resolution. Perfectly. So the fact that I didn't buy new monitors when I bought here, it benefited my all-in-ones. Some all-in-ones do have a video input. I'd like VGA or could just use it as a monitor. But a lot of them do. Moving on from desktops, we go down to notebooks/laptops, and these are really overall designed to run off some sort of battery. Can it be as powerful as a desktop? Yes, you can get laptops that are powerful as most desktops. Not all, right? It's really kind of sad. It's like, okay, you can put a 3080 in your laptop and a 3080 in your desktop. The desktop 3080 is so much better because it can have so much more cooling capacity and power delivery capacity. That even though it might technically be the exact same card, it's not going to run to the same capabilities in that laptop. You really want to push every screen or every processing power in your computer, the desktop is going to be there. Laptops for the exact same performance, they're going to be more expensive. They are manufactured down to a specific size, so they're not going to be as good as the desktop. Now, you might have some extra features built in. You might have a webcam built right into that laptop. Most things probably have wireless network built in. This goes on, fingerprint printers, those types of things are all starting to be laptops. Now, when it comes to laptops for portable use, I'm a big fan that are touchscreen. Personally, I think all laptops nowadays should have touchscreen. Convertibles, more specifically, they do allow you to fold flat or take the screen off type of thing, so you can basically use a tablet instead of a traditional laptop. But basically, to me, any laptop nowadays should have touch. You ever use a laptop with touchscreen? So it makes sense. We do it on our phones. It's easy to do, and it's very easy to understand. We do have convertibles. We also have tablets, which are mobile devices. They just traditionally had LCD displays, but they might have an OLED display at this point. And one of the big benefits of tablets over your laptop or notebook or whatever is you probably have a much better battery life. Newer laptops, especially like Macs, forget the version that goes now supporting processor. They are starting to have extremely long battery life. Definitely a big benefit. But it's a mobile device, traditionally on the smaller side for tablets. 7, 8. The phone screens are starting to get to be tablets. Especially but anyway, tablets, not really going to have a keyboard, touchscreen, probably no Wi-Fi, really good battery life. Now, when it comes to operating systems, we have four main ones that you're going. You have Windows, which is the most used operating system there, which this is as when I made this PowerPoint, right? We also then have the Mac OS, which is built by Apple, and these people favor Macs because they're more and stable, like that. I'm not going to say actually they're any more secure than Windows. They're just used by less people, so there are less known holes in the security system. People are going to go, well, I can write a virus that will affect 75% of all computers. But I can write a virus that's going to affect 15%. What about you? If I was going to spend my time writing a virus to try to make me money somehow, I'm going to much larger, much higher. So that's why Windows is the one that gets attacked more. There are still issues. Not like, oh, it's perfect. So with Macs, they're about 15%. I don't know that one. Then we have Linux. All right, Linux is mainly used to run servers. Right? Are there desktop versions of Linux? Yes. All right, probably the biggest, most well-known is UB. You also have Mint, Ali, Aura. There are a lot of different versions out there. So mainly, they are going to be used on servers. Can run desktop. We have about 5% of population. However, if you actually look at like servers running Linux, that is a huge percent. Most servers are running Linux. And then the last OS we'll talk about is the Chromebook. This is one that has gained in lots of popularity. Chromebooks are, as the screen says, very inexpensive. That's their big claim to fame. It used to be we had netbooks that were running Windows, and netbooks were these pieces of junk computers that were extremely small, extremely processing powered in size. Chromebook of Windows. But Chromebook runs Chrome OS, and they're traditionally lower hardware. not always. You can get very, very powerful Chrome. I don't know the big benefit of going to the super powerful one. But basically, they're designed to access websites. That is their whole aim to be. Want to browse the internet, maybe use a few apps like WordBook, word processing, or something. Chromebook is all you need. Right? They are extremely simple devices. But I think one of the big benefits is traditionally they're some of the downsides is they are cheap. Right? Some of their hardware and things like that. It's definitely something that in the long run, most Chromebooks require internet access. I'm going to do this. Oh, you can. Oh, we'll do that. Now, normally, where we live in, there's Wi-Fi basically everywhere. Right? But there is also many times where you may not have access to Wi-Fi, or you don't do use the data plan on your phone, from the Chromebook, those types of things. They are not a perfect end-all computer. And my notes say that Chromebooks are about 2-3%. Now, where Chromebooks are huge, and those who came from Washington County know this, public school, that in schools, that is where Chromebooks took off, and that is what Google kind of pushed for that. They were like, okay, we're going to sell Chromebooks to schools for extra cheap. The reason being is, if we can get all these high school students hooked on Chromebooks, have that be the main device they use for, 12 years that they're in school, probably might not have. But if we can get them hooked on Chromebooks, then when they go to their real world jobs and IT goes, hey, what type of computer do you want? They're like, oh, just give me a Chromebook, because that's what they're used to. So that is what Windows does. That was Google's hope that we're going to sell a boatload of these. So everyone. Some other personal computing devices, we've got smartphones, all right? Defining personal computing power with cellular access, Slight connection. We've got apps, large capabilities there. You have e-readers, all right? If you are a big reader, I highly suggest reading on your phone compared to an e-reader is absolutely. One of the big benefits of e-reading, I thought Mr. Siegel, is you can store tens, hundreds, thousands of books depending on the storage on that device. And the books are on this device that's the size of your phone. Now you're like, well, yeah, I can install it on my phone too. You are correct. But the screen on e-reading is the real selling point, right? It uses what's called e-ink to display the text and there's battery life. So e-readers traditionally, instead of telling you the battery life in a number of days, often find the number of page turns that the battery will be. You might be able to go like, I could read books. Oh, you might get a day's use out of it. It's huge energy saving. Plus, because it's basically pulling to the screen or pulling away from the screen, meaning that they're able to send them and stop using power, they turn them off. Beautiful. So I do highly suggest that if you're a big reader and you travel a lot, invest in. And they're also in theory they're not backlit. So yeah, so that's actually much better for your eyes. I would suggest, if you're just bored and you're bored that has go look at that, press the page button. A lot of the newer ones are what they call inlit instead of backlit. So lights come instead behind it, and that's better for your eyes. It's also how they do sensitivity. So we also have for GPSs, which I'd say kind of gone from the wayside. GPSs, they were just building GPS in their cell phone has GPS is not it's still used extensively, but it's not places you can find GPS, scientific equipment, cars, airplanes, boats, cell phones. If you're bored and you want to use multi-million-dollar satellites to find Tupperware hidden in the woods, what's called geocaching, where people post GPS coordinates for these things that are hidden out there. And you can go out and find them and put your it can be a fun activity to do, especially if you're in a line. Like, okay, I got 20 minutes to waste to see what geocachers are. It can be a very fun activity, especially if we've got video game systems. This is a computer designed to play games. And way back when, like the Nintendo era, the regular Nintendo, those were not, I mean, they were computers, but they weren't but like the Xbox. Xbox and PlayStation, those are just computers that have focused on computing. Like the old PlayStation, PlayStation. But oftentimes with these video game systems, you can also play movies, music, and you play online games with people all over the place. All right. Virtual reality. All right. I don't know if any of you guys have had the opportunity to experience this. Someone says PlayStation's a game. All right. But anyway, virtual reality. This to me is definitely a really interesting area. It is something that I always want to be basic. We're just not there. I've experienced the Oculus Rift 2 or something like that. Not where I want it to be. There's a lot of places that oh, it's this, it's that, it's this. I've used it and like how I interact with it. I'm just not. But still, it is a very interesting. I highly suggest that if you ever have the opportunity, it's a whole new world, basically. Now, to go along with virtual reality, we also have reality, which is the same as VR. So in VR, you put the goggles on, it's just free break in your eyes, it allows you to see things. And you're in this virtual world. That's all you see. With augmented reality, you're taking the real world. It could be that if you had AR glasses, you could walk around and do facial recognition who was around you with like their name, their head, so if you didn't know their name, you'd be like, my God, how are you doing today? Oh my God, well, you know my name. But it would still allow you to do that type of thing. Okay, I need to walk down the street to donuts. Coffee. Instead of you having to look at your phone and have to tell you left to right or whatever, right in front of you when you have to it. There's a lot of cool possibilities here. I don't think now, to go kind of go on with the single users, we also have multi-user computers. Most multi-user computers are going to be a server of some sort, a device that provides services to multiple clients. Servers traditionally they're going to feature centralized resources such as file storage, processing, and the size of your server. If I have a big server, you can size that up to fit the need of your company. Now, you can have extremely small servers, or you can have extremely large servers. Or, like for me, I actually have a server running at my house. It's small, it's an old desktop. But it fits the needs of my house. It actually over. But it's what I had laying around. Hey, let's do this. All right, and it allows me to have network storage and save everything like that, so I be on my desktop to access it. Be on my servers. So in, allows my automation stuff to work, my media server to work, photos to be backed up between my main computer. It gives me a lot of capabilities like that. And traditionally, your server is going to be much more powerful than needed. Do they have to be? Again, no. And so someone just asked, are multi-user computers always very large in size of one? Yeah. All right, so a server could be one of these racks. So that's one server might just be that little bit. And this is just, server after server after server. So this would be a very large company. But, for a small family, one row on that is all you would need. Really comes down to what you need. And you might have a server, like one of these racks. This one top one could be power. And the rest of this could basically just be storage. It could just be all hard drives. It might just be all hard drives just going straight down there. You might need some processing power to go with those hard drives, so that way you work as fast as possible. But still, you grow these servers. I'll tell you right now, each You build it to what you need. So yeah, we can scale that, and the cost of servers increases the size. Um, so yeah, and there are some companies that are doing like servers, off-site servers. So you're like, okay, Google, and not Google, Amazon, like, hey, I need a server for this purpose, and they will rate you on their server, like your own server space. Pay them per month based on how you're accessing. You don't necessarily have to have your server. There is a lot going on there. Now, to go along with servers, you have clients. That's the person who's accessing. Your computer would be the client. Servers also allow us for easily upgrading software and like that. So there's a lot of good. Common services include internet access, email, file servers, print services, and the whole virtual desktop interface. I think you guys last class, if you're using Mac, main computer is a Mac or an iPad or a Chromebook, I highly suggest that you use a virtual computer lab. All that is a virtual desktop interface. So all that processing happens on the server, but as far as you're looking at, it's a single user computer, right? So it's just one server that's splitting part of its resources off to each different person that's logged in. And the big benefit of VDI is one image or two images that you log in, it uses that image. And the benefit there is that so when IT has to update something, instead of having to go all over campus to update 500 computers, they can update one image, which then log out, log back in, you get a new image, you get a new information, you have a new software. So lots of benefits to those VDIs. You have mainframes used by businesses with massive amounts of data to be processed, and they can support thousands of users simultaneously. Supercomputers, which perform specialized tasks such as weather forecasting, biometric research. Now, one of the most interesting ones to me is it could also be called grid computing. But basically, what you can do for this computing is you can either volunteer, most of them are volunteer, most of them are volunteer, and that is you can say, okay, my desktop, I leave on 24/7. I hope you don't, but if you do, so what we can do with distributed computing is leave my computer on all the time. It sits idle, like when the screensaver turns on, the screen goes off. Night processing power can now be used by some organization to process these. One of the big ones right now is SETI at Home. So SETI at Home project analyzes radio telescope data to search for extraterrestrial intelligence. So there are mass amounts of data that has come in from these radio telescopes or gene research or whatever. We just don't have enough processing power to actually solve, or these companies don't, especially the nonprofits. So what you're doing is you're basically volunteering yourself. Now it's not yourself; it's your computer and your electric bill that you're volunteering to help these companies out. So you're paying for electricity and the capability to use your computer, but then help them process. It's huge. This took off a lot with COVID because all the COVID vaccines that a lot of people that would do. Okay, we all have our computers on anyway, but I'm not using it for work. Go ahead and use it to help try to figure out the COVID vaccine. But it's really kind of a quite really understand. Distributed computing is really a neat thing as long as you're willing to pay with it. I like just using someone else. All right, and my last slide is safety and use of technology. Ergonomics is going to be really important. Ergonomics is a study of the relationship between the worker and the workspace in an effort to reduce illness, muscular skeletal disorder. I'm pretty sure that COVID got in. If we notice in this picture, this person looking down on their mom. And one of those things that the tech kids, and it never bothered me until I was working from home constantly. I used to have my monitors. I have a tall desk. Basically, it's a standing height desk. I do about a tall chair that I can sit on to sit at the desk when I work. And I had my monitors down to the wall, so standing, they were at eye level. If I was sitting, I had to look up slightly. A whole lot up, ever so slightly. And that, I think, messed up my neck. I have no proof behind this or anything. Actually, physical therapy to figure out what was going on. Down in the arm or side. It was not fun. Um, and at one point, someone was like, "Oh, that could be your neck." And once they said that, I remembered the whole like, you're not supposed to look up at things. Now, some of you, especially if you're really short, you're used to looking up. You know, especially like our kids. You know, kids who are 4 feet tall or whatever, they want to look at me, they have to look up. Head back. For me, I am 6'2". There are very few people that are taller than me. I'm not saying that I'm less than me. I'm saying I physically, like, look at my wife, who's only 5', about a foot shorter than me, so I'm only 5'2". I physically have to look down to look at her face. But so constant looking up, looking at my computer monitors, I think you do need to make sure that computers and things like that work in a good ergonomic way. You can see here we've got like lumbar support, make sure your height adjusted well, shoulders resting on armrest, it's very good spot. This actually like, look at a whole bunch of different keyboards and ergonomic keyboards and ergonomic mice. Most ergonomic mice actually turn the mouse like they the buttons are on the side, often it's at the bottom, but here better. Especially when you're going to get a lot of time. Make sure that you're good for or at least adjusted to. Just kind of something to be aware of. All right, do I have any questions? All right, well, that is all.